Gentlemen, welcome back to the shrine. It's been a hot minute since I dropped the proper video, being up to my eyeballs wrenching on this tappet forging shit show. And let's be honest, unless I'm yammering about hair dryers, my long form videos only pull about 150 views. That's barely enough to keep the lights on in this shop. Although YouTube never paid me for this ever. They just keep moving the goalpost, you know, once they need 1,000 subscribers, once they need 1 million views on the shorts. So grab a cold one and let's get into the next chapter of the tappet forging shit show. You might remember me hacking away with a 5-ton log splitter. There's a link down below. I was trying to play hydraulic press on a budget. Just picture me shoving a hard tool into some kind of piece of metal, like a frickin' caveman blacksmith. Worked as good as a fart in a windstorm. You know, extra setup time, milling the pocket, and then I had to add milled alignment features on the bottom so that when I heat up the part and then shove it into the tool, it is aligned properly. Because I tell you, brother, when this tool comes down and this is white hot, it's gonna go in no matter what. And we are going to end up with something like, hold on, something like this mangled mess. So you can see that tool descended and it just mangled the piece, and that pocket, that cavity, is not up to snuff. Here's another one. So this is what happens when the workpiece is not oriented properly in a tool and it's heated up, and the tool's gonna come down, it's gonna descend no matter what, and it's just gonna make scrap. So I had this brilliant idea of forging the pocket at full depth without pre-drilling, machining, or doing anything else. So I take a piece of 7/8 8620, like so, cut it to size. This is about 1.5 inches, and then heat it up, and then take the tool and just shove it into that. Great idea, right? Well, it was obvious from the get-go that the 5-ton press is not gonna get me far. So this one was done with the 5-ton press. And then this is the roller that would reside in that cavity. You can see it's 17 millimeters. Now watch this. When I pop it in, you can see the end is sticking out. So that's not good. You can see that there is some artifacts from the drilling. So the tool that descended and created the cavity was not parallel to the drill. And so if I'm using a 1/4 inch drill, it's gonna have an artifact there, which I'm not liking. So a logical idea was to improve on the process. And so because the 5-ton press did not give me that tonnage, I just went out and acquired a 14-ton log splitter and basically started the whole process from the beginning. So here's a laundry list of upgrades I slapped together to make this forging rig, you know, less of a dumpster fire. So first of all, it's a vertical press. I ditched the horizontal nonsense for a vertical setup. What happens is when this piece is heated up to white hot, and then I pop it in the tool horizontally like this, it will flop down. Why? Because, you know, I need to leave clearance underneath, because when the part is forged, it's going to mushroom like that. And so you cannot put in the cylindrical cavity, or, you know, something that is holding from underneath like this. And so the horizontal nonsense just didn't work. So I had to go and create a vertical setup. I built a custom frame to bolt this 14-ton bad boy upright, and you can see that it's a pretty sturdy frame. I tweaked the tooling, you know, I went through a few rounds of grinding and cussing and reworking the forging tool and the stationary dry, you know, trial and error, mostly error. So I decided to go and achieve a deeper stroke. So this was the original tool. You can see the tool part is 28.4 millimeters, and then this is the new one, 38.4 millimeters. So a full 10 millimeter extension to the tool, longer stroke, deeper poke. This is what the new tool looks like today. The next thing that I worked on is the reverse stroke. I figured out early on that when the tool penetrates into the hot part, what happens is this guy is white hot and it's dropping heat into the tool. Essentially this tool is acting as a heat sink, so this internal cavity is cooling down, and when it's cooling down it's shrinking and it's becoming stronger and stronger as it is cooling down, and this guy wants to seize onto the tool. That was one of the first things that I found, and I was kind of doing everything to mitigate that or prevent that. You can see in a previous video I was using a lever arm to yank out the tool from the workpiece, and then there was a reverse spring that finished the job. Well, that didn't work for the latest trial, and then I figured out that the new log splitter actually has a reverse stroke. So if I pull the lever up, it is gonna yank out the tool from the workpiece. How convenient. So I redesigned the bumper. So now the bumper is bolted to the wedge. So in the compression stroke it's being supported by the wedge, and on the bottom I installed a plate and a bolt so it cannot pull the bumper off of the wedge. So when I'm exercising the reverse stroke, everything just works out. It is pulling out the tool from the workpiece. The upper part of the tool acts as a wiper, so when the forging tool is retracting, the workpiece is going to bump into the upper tool and it will prevent further movement. So the tool is going to come out of the workpiece. And this is a real important lesson that I learned. One of them. As far as heating up the workpiece, I created a spinning pedestal. The point is, I don't need to hold the part with my hand, you know, standing there close to the inductive heater. I can just put this on, flip on the switch, and then it's basically spinning, rotating the workpiece, and it also leads to a more uniform heating of the workpiece. So when it's all done, I can just grab the workpiece with my special pliers and then pop it into the lower forging die and Bob's your auntie. The other thing that I modified is that I'm preheating the lower die. So as you can see here, this is the lower die and it's sitting on the forging press, and then I just take the preheated workpiece and then pop it in. You know, most of the times it sits there straight. It doesn't sit right now because you can see there's some damage to the lower forging die. I'll talk about it later. So I just pop it in, shove it in, exercise the tool down and then up, and it's done. And you can see how, for example, this one, which is almost a successful one, pops in there and it sits there neatly. Now this lower forging die went through a couple iterations. So this one was the first piece, and you can see that it has a fairly large taper, so when I pop in the part it just falls through like that, because this diameter here is a much larger than the workpiece. And when I started forging these parts, I realized that the part is cooling down rapidly. Obviously this part, this lower forging die, was at room temperature. And so I had the brilliant idea of lining the inside of it with glass fiber insulation, something like this. This is the glass fiber insulation that the Harley people use on their exhausts. So they just wrap the exhaust in this insulation. So I thought it's a good idea to line the inside of the hole. Well, let me tell you, partner, yeah, it didn't work. And it also led to basically scrapping this tool because now the hole is oversized, and even if I pop this in, you know, it will just mushroom the part. Next time I forge something, you know, it will just mushroom inside and it's gonna be scrap. So I had another brilliant idea before that, is just to have a lower die like this, and you can see this size here, just slightly oversized. So what's going on here, this is 7/8, so that's 22.2 millimeters. And so when I heat it up to 1000 C, it will become around 22.45. So, you know, it's logical to drill this hole out to 22.5, maybe 22.6, you know, just to have a little gap there. And you can see that this sits there neatly. You know, it goes into the hole with a little gap, and for most of the time it holds it vertically. Well, that's when I got this guy here. It just completely mushroomed it, and it went sideways. And then I tried another one, and that looks like this one. Okay, so here's just a comparison: the original one and then the mushroomed one. So this is 22.2. Then this one is 33.8. So obviously that wasn't successful. So the next thing I've done is, and you can see a lot of this on the short videos when I'm making these parts. So, you know, decking the part and then making the radius so that it matches the radius in the tool, which is a necessity, right? Because, you know, I can make a sharp corner in a tool. And then the next thing is setting this up in the 4-jar chalk, and then coming in and drilling this hole. Now the way I've done this latest one is that this lower 1/4 inch long or 6 millimeter long part is cylindrical. So when I pop in this this workpiece, it will sit there straight. It will hold it neatly. And then this upper part has a certain amount of taper. The only problem with this was that when I was drilling the hole here for the handle, you know, I didn't want to have a through hole, but somehow Bozo visited the shrine and the drill just popped through. And then I'm like, okay, well, I just tap it, and then I fill out the hole with the screw, with the material of the screw, and then I just file it. Yeah, it's gonna be fine. and then the first part that I forged just got stuck in it. And you can see the residual of the hole. So this part basically was pushing on the threads, and it just got stuck in this hole. And so I had to use a big hammer to drive it out. And even in that moment, it didn't dawn on me that Bozo is the king. So I went back and then I forged another one. Somewhere here. Not this one. Okay, yeah, here's the other one. So you can see that it also has that imprint. So this part of the workpiece essentially went into the die. That's no good. Oh, by the way, this was the first one, and you can see when I pop in the roller, it's sticking out, so it's not perfect. And then I adjusted the throw, and then this is the second one, and you can see that it created a full depth. So this would be a good part to start machining. So one of the improvements I've done is I set up a camp stove and I'm preheating the lower die. And then the idea is that when I start the forging process, obviously there's going to be heat transfer from the workpiece into the die, but because the die is, you know, a couple hundred degrees centigrade, that heat transfer is gonna be reduced so that the workpiece is not gonna cool rapidly. And you can see the blue tones on this, so that means that this was heated to, you know, 350 maybe 400 degrees Celsius. So the next thing I worked on was the forging tool itself. And again, there's some video here about the machining of the part. It's done on a CNC. So first the machine comes in and it's gonna go and create some roughing passes, and then it does a couple finishing passes, so it creates this shape, and then I turn it 90 degrees and then make sure it's level, and it does the same thing. So that's how this shape, this form is created. And then I come in and then I just dress these radiuses, and then after that it's heat treatment time. So this one is 01 tool steel. So what I do is I heat it up with the inductive heater, basically red hot, and then I dunk it in oil, and that was that. So that's how I did the initial tool, which was only 28 millimeters long. Well, because this is 38 millimeters long and it has a tendency to get through hardened, you know what happened. this is what happened. So this was one of the tools, and then this is the tongue part of the tool. And it didn't break on the press stroke. It broke on the retract stroke. So when the tool was retracting, this just broke through. You can see the entire thing is through hardened. So thanks God I had the second tool back then, so I went ahead and I tempered this. So what I've done is this was sitting in 200 degrees Celsius for 2 hours, and that's basically the tempering process for 01 tool steel. By the way, when I was forging this first part, you know, this workpiece completely got locked on the tool, and that's how the tool broke. So I went ahead and then I cut the workpiece or the component in half, so that I can free this out and then see what went wrong. And you can see that the saw cut into this, but it doesn't matter because this was already annealed. So when this broke into that, this was like, you know, red hot, white hot, and it just cooled down slowly, and it essentially annealed this tongue or tip of the tool. And by the way, you can also see how the cavity looks like after the forging process. So even in this case, you can see that a portion of the workpiece got hot welded to the tool itself, so that when the tool was retracting, it was making that cavity bigger. So here you can see on the side view that it's much wider than it's supposed to be. So the tip of the tool should be around 6 millimeters. This is 8.5. And then here in this back section it should be around, you can see it's around 7, and then the tip is about 8.6. So clearly there was material transfer from the workpiece to the tool, which is not good, especially if I just use it one time. So because that happened to the O1 tool, again both of these are O1 tool steel, I went ahead and looked into what would be stronger. I found that H13 tool steel has better high temperature performance, and so this is an H13 tool steel. It was made with the same process, and you can see that there is material transfer on this one too. I don't know at this point what to do. From all that I said, all that 9, maybe 10 different improvements, everything seems to be working, except maybe the lower die. I just need to make a new one that doesn't have a hole poking through, and just maintain this geometry, because that was giving me a really good performance. So again, this part was made with the O1 tool steel, and you can see that it has a nice uniform pocket. The roller is sitting there fully. I mean, it has to go down maybe 0.5 millimeter, maybe 1 millimeter, but I can do that by adjusting the depth of the stroke. And then this part measures about 7.1 millimeters at the tip, so that would be a reasonable, acceptable solution for this. Oh yeah, a couple side notes. So my buddy said that, hey, why don't you try to forge aluminum, see if aluminum works. Well, this was the first aluminum part that I forged, and when the thing is running, the inductive heater is cranked up to maximum, and I'm looking at the timer on the inductive heater. And so as the timer goes up, I'm looking at the time, and I know how many seconds I need to go. Well, it turns out that aluminum doesn't need as much time as the steel, because this one just melted completely, and it dropped one drop of aluminum on the floor, which was scary. It's got a really good penetration, as you can see. The roller just it will get lost into that pocket, and then here's the other one where I didn't heat it up completely, but looks like this also went a little sideways. Here I am up to my neck in broken tools and half-baked ideas, thinking about ditching this forging for a blade type tappet design. So this is what the finished tappet would look like. This was done with the previous tool and a previous machining process. So if I use a blade type design, I would just machine off this entire region, and I can do that by just coming in with the end mill and then just milling it through. Now, the drawback of that design is that when the tappet is working, there's high pressure in this and then in this area. And so if I cut this section out, there will be even higher pressure in these areas. And I really don't have a good grasp of what is the highest pressure that I can allow in this design. According to FEA analysis, that maximum is between 5 and 10 megapascal, and the average is about 0.5 megapascal. Again, this is gonna be hardened steel on aluminum. So if I go with the bladed design, I can just mill it from a stock. That will be basically just turning and milling operation. And again, the downside is higher contact pressure on the tappet and you know, inside the housing bore. It might wear out the housing faster. So stay tuned, because I ain't done beating on this dead horse yet. And if you have some comments or hot takes, just drop it down below. See you on the next one. Bye.